So sometimes we're interested in determining the minimum number of trials that we have to perform in order to get R or more successes. So these are called quota problems, and they're kind of the opposite of what we've been doing. We've been given a number of trials and trying to find the probability of getting R successes. Well, now we're going to be given the number of successes and a probability, and we want to go backwards and find the number of trials necessary to produce that. So this is problem number 20, I think it is, in section 5.2 out of our book, 12th edition of Braves and Braves. And it says the probability that a single radar station will detect an enemy plane is 0.65. So for just one station, there's a 65% chance it will detect an enemy plane. But now, how many stations are required to be 98% certain that an enemy plane flying over will be detected by at least one station? All right, so what we want is how many stations would we have to have in order to be 98% sure that we can detect this plane? So let's set it up like this. I'll write it up here at the top here. We want the probability of, at least one, I like to write in English, at least one detecting, and I want that to be 0.98. All right, so I want to get the probability that we get at least one radar station detecting the plane to be 0.98. Now, the probability of getting at least one, let's translate it. This is the probability that X, the number of successes, is greater than or equal to 1. And you know what I'm going to write here? I'm not going to write equals 0.98. I'm going to write greater than or equal to, because we want to be at least 98% sure. Even though the problem itself says we want to be 98% certain, we want to be at least 98% certain that we get that. So this probability that X is greater than or equal to 1, we can stretch that out into exactly's like this. How can you be greater than or equal to 1? Well, X could be what? Could be 1, or 2, or 3, or ... And we want that to be greater than or equal to 0.98. So a question for us then is, what could the value of n be in order to get this happening? So our problem is to find n to make this work. We know for sure that n cannot be 0 because you've got to have at least some trials, right? N is the number of trials. You can't have 0. It can't be 1 because at 1, according to the problem, a single radar station will detect a plane at 0.65. Right, now we want at least 0.98, so 1 doesn't work. So this is going to be a guess and check here. So what we're going to do is we're going to try, first of all, n equals 2 at p equals 0.65, right? The probability of success being 0.65. So check in the binomial probability table. Now, when I look at this table, we have it set up like this. You have an n, then you have an r, and then you have your p value over here. So we're going to be looking in the 0.65 column, and the first n we're going to look for is 2. Now, for 2 trials, you could have 0, 1, or 2 successes. Now, what we're looking for is, back up here, we want what? 1, 2, or 3. Now, at 2, it's not going to go higher than this. So it's not going to be 0 because we want at least 1. All right, so we're going to look down here and follow this over. Okay, I'll follow it over, follow it over. We don't want 0 because 0 is not up here. We want it at 1 and 2, and it only goes up to 2. So when I look at that table for those values, now let me check this, make sure I get the right one. I'm saying 0.455 and a 0.423. Then what I'm looking at here is, what is the probability that x is 1 plus the probability that x is 2? All right, so it's at 0.455 0.55 plus 0.423. And when I did that, well, we can do it right here, right? We'll get an 8, a 7, and an 8. So we get 0.8, 7, and an 8, which is less than or equal to 0.98. So n equals 2 is not enough. Right? We're going to need more than 2 of these radar stations. So we'll try n equal to 3. So at 0.65, our table looks like this. We've got an N, an R, and then we're over here at 0.65. So N is going to be 3 now, and successes we could get 0, 1, 2, or 3. You know, let's not put that so far over here. How about at 0.65? All right, now I'm going to follow this over at 1, 2, and 3. No zeros, right? Because we want N has to be bigger than 1, more than one station. Now, what we're looking at here is what's the probability of getting a 1 plus the probability of 2 plus the probability of 3. That's equal to, okay, just add those up. And when I add these up, I'm getting 0.958. Okay, that's still less than the 0.98. Okay, so n equals 3 is not enough, but we're getting close. So let's try n equals 4. Now at n equals 4, things are going to look like this. Our table looks like this. N, R, now we're still at the 0.65 column. So at 4, we've got 0, 1, 2, 3, 4 successes. And I'm going to follow these over at the 1, at 2, and 3, and 4. And the values I get, I'll just write them in. So I wrote those values in. So at 4 trials, 1 success at 0.65, probability of success is 0.112. 2 successes, 311. You can check the table yourself to make sure that I've got these right. Now, what is the probability of getting 1 or 2 or 3 or 4 detections? Okay, well, if I add these numbers up, I get 0.986, which finally now is greater than that 0.98. So we've got it. So let's claim now, let's answer that n equals 4. And our question is this. Now I'm going to go back to the question. Watch your head here. The question is this. How many substations are required to be 98% certain that we'll detect a plane? So what we're saying, I'm going to go back to the last page. We're claiming that 4 stations are necessary. Now there's a part B to this problem. It says this. If 4 stations are in use, so if n equals 4, they kind of gave us the answer there. Find the expected number. Okay. Find the expected number of stations that will detect. Almost readable. Well, we know that the expected number is mu equals n times p, right? In a binomial distribution, the expected number, mu, is equal to n times p. And for us, 4 times 0.65 is, go to my calculator, I got 2.6. All right, so we would expect about 2.6 stations to detect. Now, of course, it can't be 2.6, right? But if we had 4 stations in one location, 4 in another, 4 in another, 4 in another, 4 in another, and we took the average of the number of detections, it would come out to 2.6. Now, if you want to see another example, we've got one here. It says the Denver Post reported that a recent audit of Los Angeles 911 calls showed that 85% of them were non-emergencies. All right, so they're reporting that the 85% of 911 calls were not emergencies. Suppose 911 operators in LA have just received 4 calls. So what's the probability that all 4 calls are in fact emergencies? What I'm looking for here is this. What is the probability that all 4 are successes? Now what we have is this. P, what is the probability of success on a single trial? That is, oh, actually it's what? It's 0.15 because it says 85% were non-emergencies. So if I let X equal the number of emergencies, then the probability associated that with is 0.15. Right, this is that 85 is not emergencies. So the probability of getting all 4 emergencies, all right, what we're going to do is this. On my calculator, I'm looking at this. Well, actually, I'm going to write it this way first. Probability X equals 4. So I'm going to go to, just to remind us how we do this, I'm going to go here. I'm going to go to second, VARs, and then that gives me distributions. And then I scroll down to A that says binom PDF, right? I want P because I want precisely 4. Binom PDF, right? That's what I'm looking for. So I press enter. And that gives me this. I get this little table that says binom PDF at the top. And then I get trials. Now, there are 4 trials. And then we want P, which is 0.15. And then we want the X value. Well, we want X to be 4, right? Out of 4 trials, we want all 4 of them to be successes. And then we go to paste, and we press enter. And our screen shows binom PDF 4.15, 4, but really the screen only shows up to here, right? Because it's so much, it's not big, screen's not big enough for all of it. Okay, then you press enter. And what comes up? Oh boy, what comes up is this. What comes up is, what, I got a 5.0625 and then an E negative 4. All right, now that E, that's scientific notation. So what we've got is 5.0625 times 10 to the negative 4. And remember, to get a number into scientific notation, you move it that many places to the left or right. Now this says, to get this decimal point right here, we must have moved it 4 places to the right. Okay, we went 4 to the right. So if I get it out, we went this way. So to get it out, I'm going to go 4 to the left. So 1, 2, 3, 4. So this is going to be point. I need 3 zeros and that 5. All right, so what is the probability of getting all 4 successes? 0.0005. So if this is really true, if it's really true that only 15% are real emergencies, this means that tens, hundreds, thousands, 10,000s, that 5 out of 10,000 calls will be real emergencies. Now let's just go to part C. It's a quota problem. How many calls would we have to get to be 96% or more sure that at least one is in fact an emergency? So what I want is this. What's the probability of getting at least one to be a real emergency? And I want that to be greater than or equal to 0.96. Now, at least one means X could be what? Greater than or equal to 1, and I want that to be greater than 0.96. So this could be what? X is 1 or 2 or 3 or ... greater than or equal to 0.96. Now we are here at the 0.15 success column. So what can we have for n? Find n. Okay, so the first thing we know is n cannot be 0 because you have to have some calls, and n cannot be 1 because at one call, where are you? You're at 15%. All right, so let's try 2. All right, so let's go over here and try n equals 2. Try n equals 2. So the table now, just go to the table. Table looks like this, n, r, and we're over at the 0.15 column. So at 2, you could have 0 or 1 or 2 successes. Now I'm just going to follow these over. It can't be 0. I want at least 1, so it could be 1 or 2. Now I need to find that table. So when I look at my table for n equals 2 at 0.15, for 1 it's 0.255, and for 2 is 0.023. If I add those up, I'm going to get an 8, a 7, and a 2. Okay, that is certainly not greater than what are we looking for? 96. Okay, that doesn't work. So let's go to n equals 3. So at n equals 3, table looks like this. You could have 0, 1, 2, or 3 successes. Now I'm going to follow this over from 1, from 2, and 3, right? We don't want 0 successes. We want 1 or more. All right, so I'm at 3, and at the 0.15 column, I'm looking at this. At 1 is 0.325. At 2 is 0.057. And at 3 is 0.003. Now look, I can tell just by looking at this, this is not greater than or equal to 0.96. All right, so 3 doesn't work. So we're going to have to try something else. Now, I'm at 3. 3 is not working. So where do I want to go? Do I want to go to 4, 5, 6? Do I want to just keep on going? Or should I try like n equals 5 or something? Let's just try this. All right, here's what I did. I looked at n equals 20, right? Dot, dot, dot. So I just went down until I kind of eyeballed this in my head. I went with 20. So when n, r at 0.15, at 20, you get 0, 1, 2, 3, 4, all the way down to 20. And then you're going to find these right here. Yeah, it is a lot of work. And then it turns out when I add those up, what do you know? It's exactly 0.96. So we need 20 calls. Now, this is not a very efficient way to do it, but it seems to be at least the most straightforward way. Right, that's a long way to do it. Now, there is a shorter way, and if you want to see it, I'll show it to you. Here it comes. This one that we just did will always work, but I think might be a shorter way to do this. Now, I've already written it out to be sure I could do it. All right, so here's what we want. Probability that x is greater than or equal to 1 has to be greater than or equal to 0.96. Greater than or equal to 1, you could have 1 or 2 or 3 or 4, so on. I want that to be greater than or equal to 0.96. Now, as soon as I see all of these, I'm going to think the opposite. And as soon as I say think opposite, I'm thinking 1 minus something. Right? Now, what is left over? Look at all these values. These are all the successes. What's the opposite of that? Well, the only one left is 0. All right? That's the only one left here. 0. So it's 1 minus the probability that x is 0. Now, that's got to be greater than 0.96. Right, now a little bit of algebra. I'm going to add this to both sides. All right, so just add it to both sides. If I add it to the left side, it's gone. Add it to the right side, it looks like this. So 1 greater than or equal to 0.96 plus that probability. Now subtract this. Right, I'm just trying to get everything on one side. I'm trying to solve for this. So subtract this. So 1 minus 0.96 is greater than this. 1 minus 0.96 is 0.04 is greater than this. Now I'm just going to turn this around. Just turn it around. So I get the probability that x is greater than 0 is now less than or equal to 0.04. Well, okay, so now what we need to do is just for the table under 0.15, so look in the table to 0.15, n, r, and you want r to be 0. So just look for this where this number is less than 0.04. All right, so you just have to check one. So you start looking through the table, and all right, here's what I see. At 16, at 16, here's what I get. All right, so at 16, look at 0. At 16, I get 0.277. Right, too big. look for 20. At 20, I'm looking at 0.039. Okay, and that is less than 0.04. Okay, so I've got it. So I only have to look up one number. I just have to perform a little algebra to get this. But it works.